gonna go ahead and get started. I know I'm a minute early, but I blab a lot, so I want to give Paul as much time as possible. Sorry for interrupting all of your fun discussions, but you can talk later and get seconds or thirds or fourths. So I'm Mariah Peterson, co-organizer of this meetup with Clint, even though he doesn't do much work for this one. He just authorizes me to spend money. So that's pretty much his job. It's like, check, reimburse. So,
I don't work at Weeb either, I just golf.
You just golf? He's the CTO here at Weeb, so he doesn't work much. Everybody else does the work. I work here at Weeb. I am a data engineer slash, I don't know, machine learning enthusiast. We have an ML guild where we're doing fun projects. We're trying to start up our donkey cars again. Yes. Yeah, we have like 7 donkey cars. They're self-driving cars that have a camera that you can teach to avoid objects and stuff. So you can manually program to do things, or you can teach them to be smart.
Okay.
Based on the strength of your Raspberry Pi processor. So.
Are you limited to Raspberry Pis?
No, you can modify however you want to modify things. Donkeycar.com.
Okay, cool. They have
Or
national competitions on Hinge.
AWS has a national competition, Deep Racer. Paul, who's speaking, is a donkey car enthusiast as well. He likes to 3D print modifications for his, so, or at least he did in the past. So yeah, just wanted to, real quick, just a little tad bit. So Machine Learning Utah is part of a larger nonprofit organization called Forge Utah. We try to support the tech community as much as possible. That means individual technologists, programmers, enthusiasts, as well as meetups. We have like 7 meetups. I could list them all, but I'm trying not to waste time. But to get more information, I will say, ask you to either follow us on Twitter and join us on Slack. Do both. Slack's most important. I post mostly to Slack. I do remember Twitter. If you have any questions, you can always hit me up on Meetup since I'm always active. But I recommend that you join the community as we post about local events not supported by Forge Utah, as well as all of our meetups, resources, articles, everything that's good, great, and wonderful is on Slack. So join the Slack. But yeah, you're all here to learn. So I'm going to turn the time over to Paul, English. He's my friend. I worked with him at a previous company, not we, but you know, we'll forgive him for that. He's pretty smart though. He knows a lot, so make sure you ask him all the hard questions. And time is yours. Oh, I have stickers too. Before the time is yours. If you want stickers, I've got them. Now the time is yours.
Yeah, okay. So donkey cars are pretty cool. Danny's got one. He got me into it. I kind of got carried away with it, and I put it away for the winter because it started to get cold in the garage. I didn't want to go out there. Now that it's the summer, I can kind of go back out there. All right, so pretty simple talk today on a complex subject. This is really just kind of a topic that I find interesting. This is not something I study or have done research or worked in. But I found a few papers in this realm, and I think it's kind of an interesting approach in machine learning and in deep learning. I think deep learning is machine learning now. Is that not true?
No.
So the topic is semi-supervision with adversarial learning. How many people are familiar with adversarial learning or GANs? A couple of you? Okay. So I didn't really cover adversarial learning, but I can kind of give you a quick rundown for anybody who's not familiar with the idea. Adversarial learning is the newish technique. It's maybe a few years old. There was a paper published by a guy named hinge. He's one of the co-authors in the popular deep learning book. The idea is to create a generator, a discriminator in the same neural network and kind of have these 2 neural networks play against each other and create a generator that generates really interesting, most often images. and use a discriminator to detect if the input that the discriminator is getting is real or fake. And so it's an unsupervised technique where you're passing both real data and fake data from this generator. And at the start, the generator is generating pretty much gibberish, but the signal that you're getting back from the discriminator provides a way to teach the generator how to generate these images. That's kind of how you're seeing a lot of techniques where you're seeing picture-to-picture translation, or the ability to generate random faces. There was a website that showed up maybe a month or two ago. It says this person does not exist.com, and you go there, it just gives you a face. Those are all GAN generated. I use that site for my Steam profile now. It's a really interesting technique, and it kind of highlights a lot of the flexibility in neural networks and kind of the expressiveness that you can get into. And one direction that they've been applied to, most often right now they're being applied to images. It's really difficult to apply them to, say, text right now. It's not that people haven't tried, it's just that you're working with a discrete space. And the generation of kind of the text is a little bit more complicated than generating continuous pixel by pixel image. So this talk is mostly about, for most of the examples I've seen in this talk, mostly related to images. This talk is about domain adaptation, and we'll get into doing this with dance. So domain adaptation is a case of I have one distribution of data and another distribution of data, and they kind of differ slightly, but they are fundamentally the same thing. So as humans, we could kind of say, like, you'd look at both sets of data, you'd recognize them as different, and you'd be able to kind of perform the same tasks on both of them, no problem. But machines don't really have that ability yet. So the idea is to come up with a way to take something from what's called your target distribution and learn from it so that it applies to your source distribution. The general idea is you have these separating kind of groups. There might be some overlap, but you want to come up with some kind of a technique to merge the two together. It's a pretty simple idea, and it comes up a lot. There are some examples are, there's a set of data called elements, so your general hello world that you learn. And then there's a set of like postal numbers that you can do. They're both the same problem, right? Recognizing digits specifically within the data set. It turns out that because there's different backgrounds, different shading, different like adjustments to the characters, if you train an algorithm on one and try to classify the other, you won't really get too much success. So domain adaptation applied to this problem would be you can train on one and hopefully get to good results into another data set. And where this becomes beneficial is when you can take a large data set that maybe you have a lot of labels for and apply it to one that it might be expensive or difficult to get data for. And then additionally, where it becomes extremely valuable is when it's nearly impossible to get labels or very expensive, in which case you might have a situation where you can synthetically generate a lot of images and kind of adapt these synthetic images into your source or your target distribution. And this is kind of becoming popular with robotics, because in robotics you've got a lot of reinforcement learning where it's really expensive to break a robot because you're trying to get it to perform a reinforcement learning algorithm and learn something really simple like move a ball, right? You can't afford, I don't know, 20 donkey cars if you're gonna have a cliff on your race course and you're gonna like drive it off the cliff 100 times before you get it right. So if you can create a simulated world where you can train an algorithm and then apply it to the real world, it helps a lot. So if you can build a model of, say, an expensive industrial robot and train it in this model 3D world and apply it to the real world, you get a lot of benefit there. Additionally, you can see it a lot in, actually the main paper that kind of got me started down this little thread of research is an application in Toyota research where they are taking synthetic driving data and they're applying it to real driving scenes. And they're doing what's called semantic image segmentation, which is where you take an image and you break it up into its component pieces. Like this is the street, these are the lanes, these are cars, these are pedestrians. You definitely don't want to have to go into a large video that has a trip around San Francisco and label every frame individually. It's just unfeasible. So this is a technique that can apply really well, or hopefully well, to that situation. Kind of another way to look at it, here we just kind of a theoretical grouping, but when you are visualizing your results in a lower dimension, you might want to see some overlapping in your source and target distribution. So the idea is that you want to build an algorithm that gets closer to the right-hand side of this visualization, ideally. So one of the interesting papers, I have a list of references, I can provide those, but I forgot to list the authors. But there's a paper out there that coined the term the SimGAN. And the idea here is you start with a simulator, and you take a synthetic image and you run it through your generator, you create a refined image, and then you use your discriminator to tell if it's a real or a fake image. Most GANs, what you're going to have for the basic GAN is going to start where the refiner, the R right there, is really your G, or the generator in GAN. And you're going to start with just a random noise vector as input to the generator, and your random noise vector is going to eventually turn into, an image or some kind of actual output that is closer to the real distribution. In SimGAN, all they're doing is they're taking this synthetic data set of eye gazes, and you're basically able, because you're synthesizing these images, I think they use the Unity image or the Unity engine to kind of generate these. You can kind of compute where your eye is gazing, and you can control your labels pretty easily. You can generate as many synthetic images and as many labels as you need. Whereas the real data case, you're going to have to go in there and you're going to have to mark where the pupil is, or you're going to have to say, okay, this pupil is about 22 degrees. I think that's right. So what these authors did was they used the GAN structure to kind of work through this problem and make these synthetic images, which are already pretty close to real, look a lot better. And from that, they're able to train a regular classifier. And now they're able to generate as much data as they need. And from that, they were able to reach some state-of-the-art benchmarks on these eye gaze data sets, as well as a few other data sets that they looked at. Any questions about this? I hope that this is somewhat simple. GANs can be kind of complex when you get into the nitty-gritty, but the idea is simple. Generating an image from a neural network and classifying whether it's real or fake. This idea kind of has grown. Let's see, oh yeah. So there are some things that SimGAN tried to apply to make this work a little bit better for them. The refiner, it takes an image as an input instead of a random vector. What they call self-regularizing loss to the refiner network. It's really just an L1 loss. And their rationale for doing this is that they don't want the output from the refiner or the generator to be all that different from the input image. And in the case of a normal GAN, you're just passing in a small vector, turns into a very large image. If you apply kind of a regularizing loss, you can control pixel by pixel how close it is to the original input image. The idea is just to penalize the large changes there. And then they created a replay buffer. I think they called it the image history buffer. This is an idea that if you go and you're trying to get into GANs, you'll start to find that they're pretty hard to train. They have a lot of instabilities, and they can blow up, and they can go all over the place. So you'll end up coming across this random GitHub repository with GAN hacks in it. And it's a guy who's put together a couple of references, early papers, and they're like, here are ways to try to improve how to get your GAN training to be stable and get something useful. And one of those was a replay buffer. And this is an idea that's maybe more common in reinforcement learning. And the idea here is you keep a buffer of historically generated fake images. And when you train the discriminator, as you're training a GAN, you're alternating between training the whole network as a piece. So end-to-end, generate an image, classify it, and back propagate through the generator. Or just training the discriminator on real and fake images at once. So your training process is a little bit more complex than the typical, you don't just do a fit, you have to kind of step through the epochs yourself and manage the batches yourself. But what you do in a SimGAN, or what they found was successful, was to half of the images that they sent to the generator or the discriminator were from the recently generated batch of refiner images, and they pulled randomly from the history. And the benefit there is that they want to make sure that the discriminator is always able to classify fake images from real, whether or not it was an early generated refined image or a newly generated one. And this kind of hints at the idea of catastrophic forgetting. What can happen is you can train a neural network on one data set, and if your data set kind of evolves its domain a little bit, it can kind of completely forget everything that it was initially trained on. And that can be kind of problematic in a lot of cases. So the idea of a replay buffer or an image history buffer kind of helps them out. And it helps out a few GANs, I think. I've seen this in a few papers, and yeah, it seems useful. And one of the last things that they mentioned is their idea of local adversarial loss. And in other papers, you might see this as a patch discriminator. The idea here is to, basically your discriminator could just say it's real or fake, just a single binary output. And you can train your loss function over that and optimize your parameters over that. And what we found that works pretty well is instead to kind of focus on pieces of the image and say, yes, this particular patch of an image is real or fake, and kind of iterate that over the entire network. And what's kind of interesting is that it's actually really easy to do this because each patch of your network is really just boiled through the convolutions of a discriminator. And so at the end, after you go through your convolutional layers, you just have a n by n vector with 2 outputs. And you're saying you're just going to effectively apply your loss over and average them together. And then your discriminator is actually classifying multiple patches over your generated real images to kind of estimate if it's real or not. And this is an idea that's found in multiple papers, not just SimGAN. But SimGAN is interesting. It's interesting. It starts with synthetic data. It gives you an opportunity to kind of apply, take an unclassified learning problem, use it in a classified learning problem, and hopefully use it in a place where you might not be able to get a lot of labeled training data. And it works pretty well. But the idea, there's a lot of papers that I came across that have this kind of idea. The next one, this was the first paper I kind of came across. This was by some guys at Twitter Research and I think a few others. And what these guys are doing, they're doing pretty much the same thing. They're taking a fake driving landscape and they are doing semantic image segmentation. So they're able to use their driving engine to kind of say like, well, this is the road, these are the trees, these are all these parts. And they've kind of added complexity to the network. So they've got the generator right there and the discriminator in yellow. Those are your traditional GAN components. But now they're adding in a target network and a privileged information network. So the target network is accomplishing an arbitrary task that they're interested in. And so in this case, it's the image segmentation. And this is definitely a difficult one to get labeled data for. You can definitely do it. There's sites out there like Labelbox. They're making it easier. And I mean, a lot of people are invested in self-driving, so a lot of people are interested in this specifically for driving, but it also applies to a lot of different image classification situations. But what these authors found was that the simulator that they're using has a lot of information that you wouldn't normally have in your labeled data set. In this case, it was the depth map of their scene. And so they found that if they could also train this privileged information classifier to learn the depth map from the fake refined images and the synthetic images, that it improved their end target network, which is kind of an interesting thing to do. And they kind of walk through some of the reasons why it worked that way. It's an interesting paper. Basically, yeah, they used the depth map. Any kind of simulated array of privileged information, you might be able to apply this technique. I couldn't really think of any good examples. Next paper I kind of looked at was this idea of learning from synthetic data. These guys are, again, they've got an F network and a G network. And these guys are taking more of an autoencoder approach, but it's still a GAN. Their F network is their basic embedding. They dive in with their real source and target image, and they create this encoded representation, which they then pass to a classifier, and then they pass it to a generator, and then they have a discriminator that they've added additional complexity to. So they're doing what is effectively the same as the patch discrimination or the patch discriminator output idea, but they've added 4 classes of output. And they've also added kind of an auxiliary GAN feature where they're passing in their, I think they're doing image segmentation as well. They're passing in their image segmentation results into the discriminator when they have them available. So I didn't look into any implementations for this. You kind of have to be careful how you train a network where you're training the discriminator on a real data set that doesn't have labels and another one that doesn't. I definitely like to look more into implementations for this or read or kind of figure out how to do this. Well, let's keep going. I've really just kind of looked through a lot of these papers, and then I wanted to go through a SimGAN example. I'll give you a hint. I worked through a SimGAN example. I generated a bunch of synthetic images, just digits, and then I wanted to see if I could get them looking like the MNIST digits and classify them. I wanted it to be like the hello world of domain adaptation. And it turns out that getting synthetic imagery to look like real imagery can be really difficult, especially when GANs are involved. But these guys also had some success in improving their classifier in semantic image segmentation using a GAN style network. Again, patch discriminator, they had outputs for source real, source fake. The auxiliary GAN is a GAN structure where it's no longer an unsupervised problem. This is where you assume you have supervised labels. By passing in the labels to the discriminator, you're classifying both for if it's real or fake, but also what the class is. So in this case, it's complex. It's the segments of the image, but it could be as simple as like, this is a 1 or a 2 from the MNIST data set. That kind of information can help propagate signal into the generator and generate images. So this is not something you can always do, right? Auxiliary GANs you might be more lucky if you can do this because you have labels. The unsupervised pixel level domain adaptation adversarial networks. You know, I think these papers did come up with clever names for their networks, but I didn't have a chance to pull them together. These guys are doing pretty much the same thing. They're using ResNet architectures, and they don't have the patch discriminator set up, but this was an earlier paper. I think this was before the SimGAN paper, but it's the same idea. They're doing a depth mapping problem. Depth map, you can get relatively good labeled data sets with depth maps if you have like a Connect or something like that. But it might not be super scalable if you need to go to a larger scale. Maybe if you want to do depth mapping with a self-driving car, this might be very difficult unless you have, expensive LiDARs. Not very feasible for a donkey car, unfortunately. One day we'll get a cheaper LiDAR. I think the cheapest one, last I looked, the cheapest one was around like $200. It's a little USB guy. Same problem, but with depth maps, they're able to get pretty good results. There were a lot of papers in this realm, and I really only had a chance to kind of touch on a few and learn a few. And I like to kind of tinker and code and get to the toy with the networks to kind of figure out how they're working. So I really don't have too many more slides, but if you guys are interested to have kind of a Jupyter notebook that we can kind of walk through SimGAN.
Yes. There is interest.
Paul, we all think your code's cool. And those pictures.
I like code. I like that deep networks make it really easy to grab the gist of architecture because everybody's making those block diagrams. You just throw them all on slides and be quick about it. So this was my challenge. Let's try to generate some fake images. See if we can turn these into the MNIST digits. I just grabbed a sans serif font and put it into an image and tried to put it in the middle of an image. And I put a few parameters for like rotation and size to try to, I guess I made it more difficult for myself. Basic MNIST loading, basic MNIST convolutional neural network. So it does pretty well when you just grab Keras and you grab it off the shelf. Like, I think this is their example. MNIST is a good starting problem. It's relatively easy. It's got a lot of edge cases that make it so it's hard to get perfect accuracy. It used to be a serious benchmark. I think in general, there are better benchmark data sets now. And so it's a good starting point though. And it's a quick, small data set. So I tried training first on synthetic data set to see what kind of results we get on the real data set, so our target domain. We go from an accuracy of 99 down to 27 just by using the sans serif images. If you're at all familiar with the MNIST dataset, this makes total sense. The handwritten digits are really messy, and there's 5s that looks like 6s, and there's 8s that look like 9s. It's really difficult to tell some of them apart, and without a label, you wouldn't really know. It kind of hints that stuff like digit recognition, it really helps to have context around it. There's some good code. This SimGAN network I found it's pretty good. It's also in Keras. This is their image history buffer. It's a boring, it's not quite a ring buffer, but it's a random shuffled history buffer that you can add images to. I tried a few network architectures. So the SimGAN paper, they use a ResNet style generator, and then they use a fully convolutional discriminator. So I tried both.
Paul, is it possible to make that font slightly bigger?
I'm sure it is, yeah.
Yeah, that would be awesome. Yeah, I like that. Anybody want it bigger?
So much larger.
Yeah, bigger, Paul, bigger. Some of the older people can't figure out their glasses.
Discrimination.
I will be sure to share this.
Thank you.
Yeah. So I said both networks. I didn't mention what the second network was. I also looked at just using, there's some examples of MNIST GANs. They're very simple. You can do an MNIST GAN or what's called a DC GAN. I just went with a very vanilla GAN. Starting with the more complex SimGAN architecture, you know, they were ideally kind of modeling it around their eye gaze problem. Slightly larger images, few, mostly grayscale, but they also had a color version of it. It worked, it trained, and there was some convergence, but it didn't necessarily work too well, so I tried a simpler, more vanilla GAN, and was able to get some convergence. I can show you some of that, but it's pretty difficult. If I were to start this fresh, I would just go for a regular GAN and see if you can just do an MNIST GAN and generate relatively good digits. I would do something like a conditional GAN where you're, instead of passing in a random vector, you're passing in a vector that represents the 1 digit, or the 2 digit, or the 7 digit, or something like that. And then hopefully your generator generates the 7 if you pass that in, right? I would start with that since it seems kind of difficult. Either the regularization is too strong and it's not able to break out of the kind of sans serif typeface into a handwritten typeface, or it might take a lot more training than I had time to do. But in general, I think the domains are far apart, really far apart, even in this human simple case. So this is the MNIST GAN. So the MNIST GAN is really just dense networks, leaky ReLUs for the refiner or the generator. And then I used a small ComNet for the discriminator. Pretty much just the same as the SimGAN version, but fewer layers, smaller sizes and convolutions. I did use the same regularization loss and adversarial loss that they had. Like I said before, they had the idea of the patch discriminator or local adversarial loss. Really, it just boils down to using a fully convolutional network, getting down to this 1-by-1 kernel size, and then reshaping it into the right size on the output. You can see when you do that, got lost output on the, oh, I remember. Okay, I separated these cells, so I generated these. I can rerun these real quick, but the more complex generator might still be running. So we'll run it. If it's not running, it's because there's again, oh, okay. So again, in the background was running. I've had this running for a little while. Here's the basic summary of the definer network. This is a simple one. You can take this generator and use a simple discriminator and generate real looking MNIST digits. But it seems pretty difficult to start with a synthetic image and move to the handwritten look. The discriminator boils down to 196 patches. One output meaning is real, one output meaning is fake. And that's what we apply the regularization, or sorry, the adversarial loss. It's a cross entropy logistic. And we reduce across each patch. The SimGAN found it useful, the authors found it useful to pre-train both the discriminator and the generator. To pre-train the generator, since it has the same input and output dimensions, it's almost like training a variational autoencoder where your input and the output are the same. And so in this case, you're effectively, pre-training is building an identity map. And then from there, you're moving into training the generator to be fool the discriminator. And the discriminator is just training the full model with your real or fake signal. So they do, I think, 1,000 steps training, pre-training of the, yeah, it should, yeah, 1,000 steps retraining the refiner, the generator, and then I think 100 steps training the discriminator. I found the discriminator to have really stable losses. So I'm not sure if this was characteristic. I don't think this is, I didn't really like this. I think usually what you see is your generator will have some success and then will die. The discriminator gets better. And you'll see the same thing, like your discriminator and your generator should kind of be battling for improving over each other. You should see some kind of conflicting loss and oscillation in both of the losses on those two. What I saw when I was training this was that the discriminator was just steadily kind of going down, and the generator was also. There was definitely a lot of variation step to step, but over several kind of batches, you can see a pretty regular trend. Here is the main algorithm of the SimGAN paper. It's very similar to most GAN training structures. You're going to take a certain fixed number of steps training the generator and a certain fixed number of steps training the whole network to back propagate through the discriminator. So here we first train the generator, or sorry, we actually train the combined model. So you can look here, combined model, we build our refiner, which we've defined above in a function. We build our discriminator. And our combined model takes the generator input, and then the output is the refiner output and combined output. So here's our discriminator model, here's our refiner model. And the combined model is what actually gets the signal back through the generator. And that's kind of it become a little bit more useful than just a random colorful pixels or something like that. The SimGAN authors originally just used SGG for their training. I like to use Atom in the generator. It's one of those GAN hacks that should help. And then, because we're using simulated data, I just created a simple data generator wrap each of the synthetic and the training set. These are the pre-training loops. Couple of parameters, and then some logging arrays. This is effectively training the generator by training a batch on the combined model. And then here, we're training the generator twice for each step and the discriminator once for each step. So here we're running through, we're training the generator twice, and then we go through, we use the generator to generate some synthetic refined images. Or sorry, this is actually just our data generator, I should say. Terminology is complex, right? Generators in Python are just yielding functions. Here's our actually refined images. And then here's the use of the image history buffer to kind of pull in kind of a bunch of images that you have seen in the past and hopefully can correctly still classify with the discriminator. We add the newly refined images to the buffer, and then we're adding a half batch of refined images just to keep it all in one array. We train on the real image batch and a refined image batch. So why real? It's just an array of ones that we've defined above. And why refined is an array of zeros. So this is common when you're training your discriminator to train a batch of real images, a batch of fake images. You can kind of get into some hacks here, but common step.
Did you only combine did you just concatenate the two different ones together?
The real and the synthetic?
Yeah.
No, we have a real image batch and a separate refined image batch. We're doing 2 training steps. Is that what you mean?
No, I'm looking up above where it says use a history of refined images.
Oh, yeah. So this image history buffer, we're concatenating the entire refined batch. And then here we grab from the image buffer, it's half of the batch size, just based off of this object that was defined. And then here, we're taking the second half of the refined image batch and we're replacing it with historical synthetic images. Or historical.
Okay, that's what I thought I saw. So then do you subsequently shuffle this batch before you train on it?
No.
That may help your accuracy.
It definitely could. Yeah. The image history buffer does do shuffling. So when you add to the image history buffer, you add it to the end of there and then you shuffle the array. So at least the second half is shuffled in history. But yeah, if you've got a block of brand newly generated images, they could easily be picked out from the rest, and it could affect your discriminator training. That's a good point. And then just a little bit of logging so that we can kind of check the progress as it goes. So this one started with 50,000 steps, and this is the simpler MNIST GAN generator and a small COMNET. And I actually kept running this until I got to about 200,000. This is probably the 4th run. But this blue line is the regularized loss coming out. This orange one is I think this is the output of the discriminator from the combined model. The real and the refined one, it'd probably be better just to average these together. It turned out that the refined loss was quite different from the real loss, which kind of hints to what the discriminator might be taking out there. And then this is from the discriminator training, the red and the purple, which are both hard to see, so I separated these out into their own plot down here. But you can see that the discriminator is definitely kind of classifying the real images, or the loss with the real images and the loss with the fake images are far different. Which is what you kind of don't want. If your discriminator is too powerful, your generator can't really learn much. The signal is like too overpowering to kind of get a good representation of your real data. So like you said, it would be good to try shuffling those when you add them to the batch, toying with the discriminator, to see kind of learn a little bit what it's learning, look at kind of things that it's getting.
Did you say you're using a ResNet architecture on your discriminator?
The SimGAN was using a ResNet in the generator and then just fully convolutional in the discriminator.
But in yours, are you using ResNet for discriminator?
It's just this simpler model is just a smaller convolutional network. The ResNet plus the larger convolutional, it took a little bit longer to train. Here is a synthetic image from a batch, and here is what the generator turns it into. And you really can't tell too much difference in here. And I wouldn't really expect to, because you're not seeing a typical GAN training behavior right here. Maybe we can peek at some thoughts of some good loss histories of some GANs after we go through some of this. But you know, ideally, you'd start to see this become more of a handwritten digit. It's a pretty, seems like it's kind of a tricky problem. I think it's definitely possible though. I went back to the original ResNet and CNN. I did start with this and toyed with it. Takes a little, this is all pretty much the same code. I just copied it into a new cell. But now we've got more of a ResNet architecture where you've got, I think, 4 ResNet blocks. Your ResNet architecture is going to pass an input through a convolution, and then it's going to append, it's going to add the output of a convolution, and I think a pooling, back together with your original input. So you're kind of able to skip a step and maybe kind of learn to skip certain convolutional layers potentially, if necessary. It kind of helps you get the deep network for some image classification problems. A little bit larger. Yeah, so this convolution activation, convolution add step is basically a ResNet block. Discriminator is just a larger convolutional network, smaller amount of patches just because you end up going through more convolutional layers that changes your output a little bit. And
Question. You mentioned the historical images. Do you think it might make any sense at all to weight the historical images differently from the generated images?
the historical images are all generated images. Some of them are just from earlier in the training process than the current step. So they should, if your generator is going to, if it's able to learn fast, then a lot of your image history buffer would be relatively realistic images. If it's going to learn slowly, you might have a lot of bad images that are very obviously synthetic. So this implementation, they just have a fixed size on their buffer, and they just exclude some of the images over time. So this implementation, it's shuffling it every time. So it's really just cutting out random images at the same time that it's adding in a new batch. I think probabilistically, you're probably not going to have stuff that's far too old in that. So you really are going to kick out most of your older images just by natural process of adding in new images and keeping the buffer size fixed. That's just memory limitations. You can probably toy with the size of that. I might actually just see, I would simplify this problem. I wanted to create the SimGAN, and I followed the somebody's open source implementation of SimGAN, which includes the history buffer, it includes the patch discriminator, it includes the ResNet architecture and all these pieces. I would go simpler to start off with, see what kind of results you can get with a simpler architecture, and then kind of improve from there. Maybe with MNIST digits, it's not as complex as iGaze or a more rich image. So you might not need all of this machinery to kind of do the same problem. You might not even need synthetic data at all if you can generate images and labels pretty easily from a generator in normal GAN. But it's a fun thing to try. So, these are just the pre-training steps again. And this one, 50,000 steps took a lot longer on this architecture. So I had this running most of the day today. And it steps through. I found over the weekend that about 10,000 to 20,000 steps, it starts to just kind of diverge pretty hectically. So this is definitely an example of some, it could be good, it could be bad. It might suggest that the network's not learning anything at all up until you get to this point, and now it's starting to overcome the pixels in the synthetic image and translate them. And when you actually generate it, you start to see that it's moving things around a little bit more. Maybe if you kept pushing this forward and training for several days, it might start to generate. It could be a good architecture. It's just difficult when you have such a long training time to know. And so if it's this complex and it's taking this long to train on a simple problem, it might be better to just reevaluate architecture to use set up to solve this and see if you can do something simpler, quicker. That typically wins out in most practical problems. Unless for whatever reason you have a necessity to, if you know that maybe you've solved this problem several times and you're trying to improve on it better than you have and beat your asymptotic limit, maybe that's when you start trying this kind of a thing. That is probably the case with Semi-Supervision. The domain adaptation is not unique to adversarial learning. There are a lot of techniques that are designed more to solve the problem of domain adaptation with either maybe like a deep network and an auto-encoding structure, or with statistical techniques to overcome like differences in your source and target domain. So using an adversarial network is just one approach. I think it's flexible and interesting, and GANs are kind of cool, so fun to try to train. This is from an early run of the synthetic data generated from the simple MNIST structure. It's got a 2.8 accuracy. It's technically 1% better than the raw fake image, so is that a success? Probably not. It would be interesting to see if you could continue training with a complex architecture, tweak it, and see if these start to oscillate and kind of, you might start to see what you'd want to see in a GAN network. You might start to see better images being generated at each epoch. It's common when you're training a GAN to save your model at regular intervals and to generate a sample of images from your generator and save those, because you kind of want to see how it's progressing. And when you're using images, it's nice to be able to look at them. Anyways, one of the last things that's probably, I wanted to see kind of how, I actually want to rerun this, but I wanted to see how the refined images looked after you kind of embedded them in a lower dimensional space. So I kind of looked at that. So yeah, orange is your totally synthetic images. Blue is the actual MNIST. So you can definitely see that like these are two totally different data sets. When you run them through a refiner, there's some grouping of the synthetic images, but you really haven't solved this problem. Right? So there's still a lot of work to go with this particular setup of trying to create some handwritten digits from some images. The most recent one I trained was the this more complex network, and it kind of, it starts to perturb these images a little bit more. So I kind of wanted to rerun this. We can just rerun this for fun, it should be quick. But t-SNE is kind of a slow algorithm. It might take a moment. Maybe we can revisit it again. But this MNIST is running. You can see if this is the exact same network as the original MNIST. It's the simple Keras example. The accuracy quickly goes to 1 on the training set, and the validation accuracy, it looks like it's oscillating kind of the same one. So I don't think we've learned anything. I don't think we've overcome the domain difference yet. I think that it would take more iterations of again, architecture to kind of overcome that. Next thing I would try would probably just be to go back to a simple like MNIST conditional GAN and try to use that as a trainer for your regular classifier, and then see if it at all gives you anything better than these. Might be really difficult. I think one thing to learn from this process is that this is a real and useful tool for solving domain adaptation, but it's complex. It requires a decent amount of compute power. You might want to explore simpler statistical techniques or something more, maybe like an autocoder technique. It might be easier to work with. And you might want to reserve this to a problem where it's expensive to get labeled data. So if for any reason, most companies, like, it's gonna, I think of all the problems that we have at NAV, we are lacking in a lot of labeled data, and I think a lot of companies lack in labeled data, but it's nothing that we can't do with Mechanical Turk or even with our own internal labeling tools, right? So we can go through and label a lot of data, and it costs us money to do that. It costs us man hours and time or people hours. But it probably will get us better return than a lot of investment into kind of tweaking this architecture over and over and over again. You might do these hand in hand, but I'd imagine that for now, if you can do labeling, it might be better. And up until the point of like financial restriction, you probably won't step into this as much. But it is an interesting technique. And I kind of like being able to dive into this because I think that we kind of need to solve these kind of problems to really scale deep learning, machine learning, and AI in general. I think we'll keep improving these techniques over the next few years. We'll start to see a lot of breakthroughs here. I think we'll get a lot better at training and implementing GANs. And I'm also very impressed with kind of the flexibility that you get with deep networks. You're able to combine and build architectures to fit a lot of different problems that you can't necessarily do with a simple supervised classifier or regressor, which is really cool. So that's kind of the walkthrough. Let's see, we did get tcmeter on. This is now with the ResNet architecture, so it looks like it's starting to kind of pull little clusters of these images together, but it's still pretty far from the target domain, so there's a lot to go there. I will share these slides and this notebook on my GitHub, and if you guys have any questions or anything you'd like to.
So for someone who hasn't done a ton of deep learning, if this isn't too big of a question, like what is the function of an autoencoder? Like, is that like a feature extractor, but by a network or?
Yeah, definitely. So it's a network, which is, it's like an identity map. So your input and your output are the same, but you want to bottleneck your network into a vector that is effectively a feature extractor. It's useful for like representation learning or for embedding. It's nice because it's unsupervised. Your input is the same as your output. So you can use it on images, and you can learn like a reduced vector space that represents your image or the important parts of it. It's useful in maybe tabular data sets on deep learning, since like a large categorical space isn't necessarily the best as an input for a network, but if you're implementing some kind of representation of your tabular records, it might work well with classifiers. And it's kind of nice because if you're using a deep classifier or a deep regressor in your autoencoder, you can kind of train them at the same time in the same network. That can kind of give you some auxiliary, some additional information. Or maybe just the vector embeddings are useful in their own.
Okay. So we can essentially think of it as a like deep learning tool for dimensionality reduction, or like. Sorry.
Yeah. So you might have like a manifold learning algorithm or like PCA or something like that, which are what I would say would be traditional dimension reduction. I would say autoencoder is probably your most common dimension reduction in deep learning.
Thanks.
Yeah, I have a question about the plot that you showed us. So there was a as the loss for fake data set is decreasing, the loss for that is decreasing, the loss for real data set is isolating. It's not it's unstable in when I see that one. How do you know? You said it's converging. What's the metric that you used? So how do you know that it's converging? I don't know.
I mean, it's not necessarily increasing. So it's converging. It looks like it's hitting some kind of asymptotic shape. And so this might continue to dip down for quite a while. But eventually, it's probably not going to get really all that low. Unless something in the network, some of the parameters in the network fundamentally change.
Oh, sorry, not that one. When you go down.
Yeah.
Yeah.
Oh, this one. There's like a bit of a delay on the AirPlay, so I'm scrolling, looking at this.
I don't think it's not that one. I think, could you go down?
Yeah, let's look at, this is the original SimGAM architecture. And yeah,
I think that one.
yeah, and this is a decent amount of steps on here. And then you start to see that like the real and the refined are definitely differing. So to say that the loss is low on the refined means the discriminator is doing a better job at picking out the fake images than it is at distinguishing the real. This was an aspect of this implementation. They are keeping track of the real and the refined output separate. Other implementations, I mean, maybe you just average these together, like keeping them separate. I don't know if I'd say that, like it seems like it could be useful, but really you're interested in just one loss on the discriminator. Okay. I don't know what I'd say given that the difference in them until I toyed with the network a little bit more.
Do we have any other? Okay, go ahead.
Oh, yeah.
So I'm not sure if this is a good question to ask, but do you run the risk when you're using this method of working in kind of an echo chamber where you're only using data that's already similar to data that you've already labeled? Like any new data it might be the right thing, but it's something not from the original set. Like let's say we had numbers 1 through 9, and also we introduced 0.
Yeah.
That
could be a legitimate problem, right? But you might have that in a supervised problem as well.
Sure.
Yeah, I mean, it's kind of like you don't know what you don't know. And in your training data, there's going to be a lot of stuff that you might not know is going to be in the real world. This happens all the time in machine learning. When you train an algorithm, everything looks good, you put it into production, all of a sudden things aren't working like you expect because your training data doesn't match what the production realm looks like. I think you could definitely have that problem here. You probably could have that in any machine learning algorithm. Whether or not it's more pronounced or not, it could be. Because maybe you are creating a higher level of like reinforcement into a particular domain and you no longer can generalize as well. Yeah, I think that's definitely a possibility.
I was just going to say, part of the benefit though is you, because you use the simulate, it's a lot easier to simulate those rare error cases, right? Ideally, it should make it easier than supervised domain to handle those because like that case where, like if you're missing 0 in the original data set, like it fails in both cases, if you could simulate the problem, like you can go through and enumerate and find like, this case is super rare, we can't find photos, we can't find video of this particular error case or a particular type of wreck or problem, whatever else you want to have go wrong. But it's a lot easier to think of things that can go wrong and put them in the data set without actually having to have a training data for it.
Maybe in Dragon you could say like, if you don't have any supervised or labeled data with columns in it for some reason, you could generate that in your simulator and label them. And again, I'd imagine that like there's a GTA 5 data set, which is a bunch of images captured from the game Grand Theft Auto. That's used because it's a gaming engine about driving. It's useful for the same problem. So you could probably take that data set, run it through, like a SPGAN architecture or a SimGAN and kind of create refined images that look like real roads and train from it. Grand Theft Auto is going to miss a lot of things that are in the real world. There's going to be a lot of things. But you can always build a simulator that might better the use case and hopefully address that. Maybe one more question?
Just on the difference between the chart, it seems to me that this could be useful specifically to identify cases where you're more accurately catching, say, the fake ones, but that's because you're saying everything is fake. Mm-hmm. So the other line would diverge from it instead of staying steady or following it.
Yep, might be able to do that. I think it's interesting kind of looking at this plot after this network is actually starting to perturb the image. So what you're seeing is that with even just a little bit of perturbation, you're actually starting to make the discriminator work here. Whereas up until this point, it's really not doing much work, right? Either it's returning the same result every time, or it's easily learned real from fake. And now you're starting to perturb the synthetic images, and so maybe it's starting to actually produce incorrect classifications on the synthetic images now. But the refined loss is a little bit lower. I would look at like examples of output from this network, maybe at different steps of the process to kind of evaluate that. Look at the parameter weights, kind of do some just normal analysis of the neural node, kind of figure out what's going on there.
If we don't have any more questions, let's give Paul the night.